All right, here we go. This is section 2.8, last section of the chapter. So congratulations on our first chapter. Let's go to full screen. The title of this, here we go. The title of this section is Graph Linear Inequalities in Two Variables. So a linear inequality in two variables. Nice, they loaded us with formulas here. Four different formulas. First of all, this is equation of a line. This is in standard form, which we talked about, right? AX plus BY is equal to C. And then they give you all four possibilities. Less than and equal to, greater than, and greater than and equal to. No big deal. So the solution of a linear inequality, any ordered pair that makes the inequality true, right? True. So if you read it like 4 is greater than 2, that would mean it is true, right? 4 less than 2, that's false. So true when the values of x and y are substituted into the inequality. We'll do an example of that. And then the graph of a linear inequality is a set of all points in the coordinate plane that represent the solutions of an inequality. That's quite something. We're going to graph those and show you, again, this is shading. We'll shade the areas that make the inequality true. And finally, a nice definition of half plane. So there are two regions of the coordinate plane that are separated by a boundary line of the inequality. So again, let's get into the examples, and I think these vocab words, these will make a little more sense. So here you go. Here's example 1. This is checking to see if solution points are this is to check whether ordered pairs are the solutions to an inequality. So the example we'll do here is check whether or not 3, 2 will make the inequality 4x plus y greater than 6. It will actually make that true. So we substitute in. For x, we put 3. For y, we put 2. And the answer to that, right, we say that is 12 plus 4, which is 16. And so finally we say, is 16 greater than 6? Yes. So this is a solution. This works. So it's, I think this second example is probably going to not work, right? That's typically how it goes. So we're going to put -1 in for x and 4 in for y. And then we'll see that -4 plus 8 is 4. And so that would mean 4 is greater than 6. Well, that's not true at all, right? 4 is less than 6. So this is not a solution. Pretty straightforward. All right, so let's see if you got it. Here's a check. Plug both these points in and state whether or not the ordered pairs are solutions to the inequality shown above. Hit pause, and when you've got your answers, go ahead and hit play. And there are the answers. So 6, 2 is not a solution, and 3, -1 is a solution. Nice. Let's keep going. So here we're going to start graphing linear inequality. So this is our steps. We have two big steps to graph any linear inequality. Step 1, we would like to graph what we call the boundary line for the inequality. And we use a dashed line when we're given an inequality that's either less than or equal to, or excuse me, less than or greater than. And we use a solid line for less than and equal to or greater than and equal to. I always remember we make a solid line when there's a line underneath the inequality. Fancy. And then we test a point, right, that is not on the boundary line. Not on the boundary line, right? We can't do the boundary line because we already know it's either less than or, equal to determine whether it is a solution of the inequality. If it is a solution, then we shade the half plane containing the point. And if it is not a solution, shade the other half plane. So we need an example. So here we go. We have this inequality. We'd like to graph it. So again, we will think about the boundary line as just simply y is equal to -1. So we know how to graph that, right? The next thing, though, we better, before we start drawing, is to look up and say, oh, this is less than only. So this is a dashed line. And again, if this had been less than and equal to, it would have been solid. So at -1, we're going to dash a line. And the dashed line represents the fact that any point on this line would not satisfy the inequality. So we need to pick a point that's not on the boundary line, and by far the easiest point to plug in is 0, 0. So everybody is going to plug 0, 0 in just to make their life easier, and you can only do that, of course, if that line is not on the boundary line. So if the boundary line goes through the origin, pick another point. So when we plug 0, 0 in, we notice, right, that 0 is not less than -1, right? So 0 is not a solution to the inequality. So I would not shade here, I'd have to shade down here. Nice shading. Got it. If you want to fill this in, this would be does not. Great. Let's do our next example. A little bit more involved. This is our line. So the first step is to graph the boundary line. I would use, again, a dashed line here because of the fact that the inequality is just a less than symbol. So graphing this line, I would do x-intercepts. I would set x equal to 0. And when I plug 0 in for x, I'm left with -2y is equal to -6. Divide by -2 and I'll get 3. And then I would also plug 0 in for y and solve for x. So again, up here, if this becomes 0, I would simply divide by 3. -6 divided by 3 is -2. Again, you could also solve that equation for y and graph the line, but I think this is a little faster. So 0, 3 is here. -2, 0 is here. Again, my dashed line, oops, I could use a ruler. Here we go, dashed, somewhat of a line. Sorry about that. Again, I need to test a point. And here in this box is exactly what I said on the last slide. It's often convenient to use 0, 0 as a test point. However, if 0, 0 lies on the boundary line, you must choose a different point. And in this case, nope, the origin is not on the boundary line, so I will use it as a test point, meaning I will say 3 times 0 minus 2 times 0. Is that, right? I should really put a question mark above here. I'm questioning, is that less than -6? So 0 minus 0 is 0. Is 0 less than -6? And again, no, that's not true. So instead of shading the region or the half plane below the line, I'm going to shade this region above the half plane. Okay, now it's getting really great, right? We're going to graph an absolute value function, which you're very good at. We did that today in class. So where is the vertex of this absolute value? So again, step 1 says graph the boundary line. So let's get right into it. The vertex would be at 1, +2, right? And then we have a slope of -3, so I'm going to go down 1, 2, 3, and down here. This is, again, a dash. They like their dashed lines, right? We should have an example where this is also equal to, but this is a dashed line. Let's see how I can do this freehand. A ruler would have been a good idea. Nice. A test point. Well, it looks like we're close to 0, 0, but I guess we're not on 0, 0. So we'll plug 0 in. Again, this is going to be 0 greater than -3. Plug in 0 for x as well. -1 plus 2. So it looks like if we do this together, -1, right? 0 minus -1 is -1. The absolute value of -1 is +1. +1 times -3 is -3. plus 2 would be negative 1. And is 0 greater than negative 1? It sure is. So we will shade this region. Right? And this is fun shading because I'm going to shade basically everything on the outside, I guess, of the absolute value function. Is that right that I say that? And the inside stays blank. So this is a solution, and we'll shade the outside. Excellent. I think you need to try a few of these. So we have 3 examples. Why don't you go ahead and hit pause. See if you can't. Be careful with your dash lines, right? Maybe start by saying, oh, these out of the 4 are dash lines for boundary and others are solid. And then good luck with your shading. Hit pause. And here are the solutions. I'm out of time, so I'm going to stop the video. Again, make sure you see that problem 3 is dashed, problem 5 is dashed. The other 2 are solids, right, due to the inequality. Hopefully your lines came out right, your boundary lines, and then your shading. If you shaded on the wrong side, really make sure you check that out. And we will practice this on Monday. See you then.